opportunity to introduce our speaker tonight. I am, without fail, I think, impressed when I look at the CVs, at the background of the speakers that we have here, and Ben is no exception to that. His 15-page CV is very impressive. He has a bachelor's in geology from UC Berkeley, a PhD from MIT. He has held positions at UC Berkeley, Lawrence Berkeley National Labs, the NPS in Alaska, and acted as an exploration geologist in Alaska, positions at MIT, Harvard, and now since 2006, fortunately close to us, ISU, over Pocatello. His research interest, as summarized in one sentence, sound like he uses a wide range of tools and techniques to focus on the physical and biological processes through which the Earth's surface responds to climatic, tectonic, and anthropogenic, that's us, disturbance. He is widely published. He has been an advisor to a very long list of graduate students. He is very active in ISU department and university level committees and programs, as well as a lot of activity with professional organizations. And of course, he teaches a wide range of courses at ISU. And finally, while he is from and was raised in California, he has close and deep ties to Alaska, including his wife, who is from a small village in the far northwest of the state. His early time there, which was right after he had acquired his UC Berkeley bachelor's in geology, led him to return, I think he might prefer this, to return to school to MIT in order to obtain a PhD in landscape evolution that he was inspired as a result of his time there. And what he has studied and learned both in Alaska and through his studies will be the focus of what he presents to us tonight. So I'd like to ask you to join me in welcoming Dr. Ben Crosby.
Thank you, John. Well, good evening, everyone. Thank you guys for having me out. It is a pleasure to be here. As you know, there have been multiple people from Idaho State University that have come out and given talks here, and I have been jealous every single time because it's a true honor. I think this is one of the places where geologists come and cannot leave because of stunning beauty, because of active landscapes, because of an opportunity for an exciting sort of outdoor lifestyle. I live on the other side of the hill, and I do have some Jackson envy, which I'm sure people around the world do. But to be able to come out and share my work with you today is wonderful. I have projects that are underway that may become relevant in the years to come. I've just worked with the National Park Service. I don't know if Kathy Melander is here this evening. No, she's the park physical scientist, and she's just collected high-resolution topographic data called LiDAR for the entire park. And that gives us topographic maps with the resolution of 1 meter. And so I'm going to meet with Kathy tomorrow morning at 8 o'clock, and we're going to talk about future projects together. And so hopefully I'll be able to maybe in the future share some of my work closer to home. But for today and tonight, I'm going to talk about something that was close to home to me for a few years, as you heard after I finished my undergraduate, a place that really changed me. I grew up in California, sort of a suburban kid. I'm the son of a geologist. And I tried to be an architect for a little while, but then I took a geology class and I said, this is exactly what I want to do with my life. And when I moved up to Alaska, I got to expand my horizons beyond just thinking about, faults and the way that we interact with landscapes and the hazards that they pose to us in large urban areas like I experienced in California. And instead, I got to experience landscapes that had not been affected by human touch necessarily, by changes in wildlife, by changes in the way that the rivers behave, by changes in the way that the land is arranged even. In many ways, Alaska is the place that you can go if you want to see what the landscapes around us might have looked like before extensive human influence. And I think it makes for a really interesting place to study natural processes like the ones that I focus on in my career, ones about how landscapes change and behave through time. And so I'm excited to present to you a small postage stamp of a series of projects that I've done in Northwest Alaska having to do with how contemporary climate affects landscape stability and how that landscape instability ultimately has impacts on things like water quality and human groups that live and depend on these rivers. And it's exciting as well to present this talk today because in the audience is Pat Calhoun. Pat, raise your hand just briefly. I'm not going to embarrass you too bad. Pat was a graduate student who worked on this project. And Pat now works here in Jackson for Biota. I don't know how many people know Biota as a consulting company here in town. Yeah. And so it's really nice to be able to sort of full circle come around and present something in a place where one of my students is able to be in the audience because this is his hometown. So anyway, that's really special to me as well. So here we go. The image that you see right here shows what is called a retrogressive thaw slump. Now the thawing, I'm sure you understand, it just means when something that used to be frozen becomes warm enough so that ice is no longer present. And slumping is the idea that material doesn't necessarily, fall, that it more flows in a downslope direction. And I know you guys have had a recent slump here, the, what's it called? Okay, I've often referred to it as the Walgreens slump or something like that. But yeah, you guys have your own taste of slumps. This one is a little different because as this material thaws, it really liquefies and flows more than behaving as a solid chunk. And it's retrogressive because the headscarp, or the wall that makes up the back of this, moves progressively back through time. The primary focus of my talk today is going to be about how this feature has grown through time and the different tools that we have to be able to measure that change. That's the primary thing I'm going to speak about. There are some other things, if I talk fast enough, that I may share with you about the sort of release of greenhouse gases from thawing permafrost, the impacts of the sediment that is coming out of a thaw slump like this one here and how that affects river ecosystems. We'll see if we get to those things. But mostly I'm going to talk about the topographic evolution of this feature right here, from its initiation to stabilization. So that's the roadmap for today. Of course, accomplishing this has not been really easy. There's been a lot of different faculty and scientists at places like the University of Minnesota, Idaho State University, Los Alamos National Laboratory, and University of Alaska Fairbanks, who have been great helpers in this project. One of the co-authors in the front was a Los Alamos employee as well. A suite of different ISU master's students have participated in this, and I've gotten a lot of help from folks at the U.S. Fish and Wildlife Service. Most of the funding that supported this work came from the National Science Foundation, as well as help from Fish and Wildlife, and Los Alamos pitched in some money as well. So I'll go from an introductory perspective and sort of zoom in on what we know about Arctic landscapes. This paper is one that I was able to be a co-author on that forecasts how we expect the Earth's surface, because that's what I study, to respond to future climate and land use changes. It's a very forward-looking kind of paper, and we ask ourselves questions about how individual systems, like how will rivers change as we go forward in time? How would sand or wind transport or aeolian transport change as we go forward in time? Hillslope stability, how will that change? And one of the other chapters that I focused on in particular was about Arctic landscapes. And though this paper is only about 12 pages long, it's open source. That's what this open lock means. So if you were to look up forecasting Earth's surface in the magazine Earth's Future, you could find this. And the great thing is that there's about 80 pages of appendices for each of these individual types of landform, whether it's rivers or glaciers or things like that. We couldn't fit it all into the paper itself. What we learned by putting together all of these great scientists and banging our heads together about what we expect of the future is that we know that the Earth is likely to respond to changing climate in non-uniform, meaning not all the same everywhere, and complex, meaning difficult to predict ways. From the paper, we came up with this phrase: in the future, the Earth will be warmer and precipitation events will be more extreme. That means that we could both experience droughts and floods. There's no silver bullet for saying things will be wetter, things will be warmer. It will be more variable. Hydrologic uncertainty will increase. Global mean sea level will rise. We know there will be arid and semi-arid regions that will become drier. In further, we also say that consensus forecasts, ones where we take multiple models and try to understand what the future is going to be like, don't really exist for how climate and land changes will likely impact Earth surface processes, how rivers work, how hill slopes work, how glaciers behave. The models themselves are not predicting Earth surface processes at this time, but rather bulk meteorological or climatological parameters, but not necessarily anything about surface processes. But based on these climatological or meteorological drivers, we expect to see nonlinear or threshold-dominated interactions between topography, vegetation, sediment transport. Now, what does nonlinear mean? Nonlinear just means that for an increase of 1 degree, let's say from an average of 4 to an average of 5 degrees Celsius in some landscape, there will be an equally proportional change in how much water comes down the river or how quickly hill slope transport occurs. Instead, there are these thresholds where we may expect to observe little change and then all of a sudden rapid change, right? And people often refer to this as tipping points, but we use the phrase threshold dominated. It's a little less loaded of a statement. And so topography, vegetation, sediment transport are interacting. And then there's also this importance of alternate stable states, meaning that what we know today may be stable under these conditions, but there may be another stable condition that we move to. And there's a likelihood of more extreme or rare events as the hydrologic cycle intensifies. Okay, so these are some predictions that we have going into the future for the global scale. And I'm going to focus in now on the Arctic. So given what we know about these sort of global scale expectations, there are clear indicators that nowhere will contemporary climate driven changes be more pronounced than in the polar regions. And because the South Pole, the Antarctic continent, is largely covered with ice and will remain covered with ice for the foreseeable future, the short future. It may thin, but it's going to stay covered with ice. Really, it is Arctic landscapes or northern landscapes where we expect to see the greatest changes in geomorphic processes, or the things that are sculpting the landscape. Why are these changes occurring in the Arctic? Well, first of all, there are large changes in surface albedo, or the reflectivity of the surface. So if you think about a snowy or icy landscape, it has a very high albedo. As that snow persists for less time, or maybe the extent of sea ice becomes less and less over time, that means that more solar radiation will be absorbed by the surface, warming those waters and warming those areas. Okay? So large changes in surface albedo occur in places that have ice and snow. Transport processes in the Arctic have been tempered in the past, or limited in the past, by consistent cold temperatures. And what I mean by that is that the landscapes of the far north have largely been places that have accumulated sediment. If you've ever seen photographs from, say, the North Slope of Alaska or Siberia, you see these rolling green hills, kind of like the places maybe Teletubbies would inhabit. It's this very bumpy, smoothed off surface. And that's because largely as plant matter grows and senesces or dies, that material ends up becoming incorporated into that soil rather than being broken down and recycled biologically within that soil column. This means that Arctic soils over time have accumulated lots of carbon. They don't have very dense drainage networks to be able to carry sediment off the landscapes. So these places largely are accumulating sediment from windbone deposition as well as organic deposition, and they're constructive rather than erosional for the most part. And the third point to bring up here is that permafrost itself, now permafrost by definition is any ground material, any ground that stays below freezing, 0 degrees centigrade, for more than 2 years. That's the definition of permafrost. And so I want you to, a lot of people have misconception that permafrost means these big, thick lobes of ice, water ice buried underground. Now that exists and that is part of permafrost, but cold rock is also permafrost. And permafrost itself is essentially an ice age hangover, right? It is a leftover from a time when we were consistently colder. And for the last 12, 10,000 years, for the Holocene, we have been experiencing temperatures well above those that existed during this colder quaternary climate. And the permafrost that we observe in northern latitudes is essentially this out of fashion kind of persisting landscape feature. And it's not really anything that has been stable over the last 10,000 years. In fact, it's been degrading all this time. It's just degrading now at a more accelerated rate. Okay? So permafrost itself is already at this threshold for stability where it's being lost. Let's look at a couple plots. These are global images from the most recent IPCC, the Intergovernmental Panel on Climate Change. And this comes from their synthesis report. This is the short version that's nice and easy to read. And we've got a couple different scenarios here describing changes in average surface temperature relative to past temperatures for the period 1986 to 2005 and 81 to 2100, both temperature and precipitation. I want to turn your attention to where the changes are most extreme. And the greatest warming are these darker red temperatures, and I want you to notice that they exist in the Arctic. This is the place where the largest change is expected to has been observed to occur and is expected to continue to occur. For precipitation, from 0 as we go into greens and blues, we see higher precipitation in the Arctic, and even more so as we go toward the future scenario. Why is this? Why is the Arctic so much more sensitive and so much more responsive? Well, the answer is that the Earth system, the whole Earth system, behaves as a heat pump where most of the incoming solar radiation occurs at the equatorial regions and is moved through both ocean and atmospheric circulation poleward. And in fact, if we didn't have this great heat pump moving energy or heat northward, the Arctic would be much, much colder than it is today, and the tropics would be unbearably hot. And thank goodness that we have this heat pump, because it makes the planet more sort of habitable to a wider degree, a wider array of places. Okay, if the Arctic is warming more, what are the consequences of this? And in this diagram, which comes from a paper that my co-author for this talk, Joel Rowland, he's at Los Alamos, and he and I and a few other people met together while I was still doing my PhD. My PhD was about studying waterfalls in New Zealand, but I was able to convince my PhD advisor that Arctic landscapes were cool and that it was what I wanted to move into. And so he gave me some time, and I got to go up there and participate in a bunch of meetings that ultimately led to this publication. In this sort of conceptual diagram, you see all the different impacts of a warming climate on Arctic landscapes. And some things, like the one I'm going to talk about mostly today, retrogressive thaw slump, have to do with warming temperatures, thawing permafrost, destabilizing the hill slopes, and causing them to fail and go in. But other ones, like increased occurrence of fire in Arctic landscapes are observed to be occurring as Arctic dries and becomes more susceptible to ignition by lightning. Now, lightning is becoming more frequent as well in Arctic landscapes because we have more convective storms or heating at the surface that causes rising and ascending air masses that lead to these kind of lightning strikes on dry tundra, which lights fires, which causes many of these things to just be accelerated. Fire changes the albedo of the surface. It makes it black, which then makes more heat be absorbed into the surface. And features like these thaw slumps or these thermal erosion or these active layer detachments, these are all ways that the landscape thaws and is being cut up and eroded away. They increase once it's been burned, of course. There's catastrophic lake drainage and other things having to do with bank erosion and sediment being produced that way as well. So there's many of these kinds of consequences for warming warming temperatures on Arctic landscapes. There's a more global concern compared to these local ones that I just introduced. And that is something called the positive feedback loop of Arctic soil thaw. Okay? Now, in this circumstance, as I was saying before, organic matter being produced on these tundra landscapes, like the area you see right here, become deposited, and these organic materials become buried progressively over time into these Arctic soils and then frozen into place. As this occurs, this freezing into place doesn't allow for full decomposition and digestion of that organic matter. Now that means that we are burying carbon into Arctic landscapes. And this has been going on for a long time. Arctic soils, in fact, hold more carbon than all the soils worldwide. They are the sink for organic matter into these soils. Okay? Now, what is exciting about this is that as temperatures rise, that leads to permafrost thaw, which takes these buried frozen materials and makes it possible for them to undergo decomposition. The microbes start chewing away at it, and as those microbes begin to digest and break down those materials, they release greenhouse gases like carbon dioxide and methane to the atmosphere. And as that occurs, those greenhouse gases then increase temperature, which leads to further permafrost thaw, which leads to more decomposition, microbes chewing away at this buried, undigested carbon, which results in more carbon dioxide and methane being released. This is what's referred to as a positive feedback loop. Warming leads to some process, which leads to more warming, which amplifies that process, which leads to more warming, which amplifies that process. This is a positive feedback loop. And this is probably, in the permafrost community, the single most important question that we're working to understand right now is this potential for a positive feedback loop. And Ted Scher, if you want to read more about this, Ted Scher, who's now at Northern Arizona, is probably one of the world leaders in that discussion. Had an opportunity to work with him over some of these projects. I'm going to hone in on this, okay? I'm not going to try to give you a global panoptic view of permafrost thaw and its implications. I want to give you a more local story, something that we can wrap our hands around and make quantitative measurements of and actually make predictive tools come out of. Okay? And I'm going to focus in on this one slump right here for the remainder of the talk. And we're not going to go global again. We're going to stay and we're going to focus on this place. And why focus on just one thing like this? Well, because it's a great demonstration of all of the different processes that I've spoke of up to now. As thaw occurs in a retrogressive thaw slump like this one here, it releases that deep carbon, which then is able to flow out, be mixed within the river, to experience digestion on the floor of this feature. Changing temperature affects the rate and style that this wall gets worn back at, and how quickly new carbon is sort of added and made available to be digested. As that material comes down into the river here, it's not only transported away, but but it itself experiences biological processes breaking that material down, affecting things like fish habitat and water quality, two things that affect villages in these areas. And so I'm interested in understanding the pace of deep carbon thaw, delivery to channels. I want to know about this topographic evolution, especially volumetric change. And one thing to know about these kinds of features is that people have studied them before. It's not the first time. I'm not the first person to come and do this. But most of the time, people have done this by looking at aerial photographs from Arctic landscapes. And in an aerial photograph, you can draw a circle and say, okay, that's, oh, where's my button? There. That's how big this feature is. And then it gets a little bigger and a little bigger and a little bigger. And we track the area that these things grow. But I'm interested in volumetric change because potentially these features, their volumetric evolution may actually be more interesting than just an increasing area over time. There may be some internal behaviors that are cool, and we're going to focus on that. So we need 3D, high frequency, long duration topographic data to measure this volumetric change, and that's what I'm going to present today. So in the feature, this is how it works. The head wall grows by back wearing or warming of the head wall, and it breaks down and collapses down, and then that material gets stored for a little while on the floor of the slump. And every now and then it gets picked up and moved, maybe sometimes as a big catastrophic earth flow kind of thing that comes out and builds the fan, or maybe it's just water trickling through. And that then can be stored in the fan temporarily, but as you see, the river here is eroding the edge of that fan, which then carries that sediment away and down in the river. But the river can't carry it too far. In Pat's work, he demonstrated that the concentration of sediment decreases as you go downstream, and that's because during low flow times, the sediment's being deposited out, right? And so it gets deposited on the river, but then when flows kick back up again, it gets remobilized, moved a little further down, deposited and remobilized, and ultimately moved out to estuarine or ocean systems in this area. I want to test two hypotheses, or discuss two hypotheses in this test, or in this talk. And the hypotheses are essentially statements of how we expect that the landscape might behave. And we're going to do some tests to check that. Thaw slumps and their head walls, like seen in this photograph right here, will have a form or a shape and a retreat rate that responds to hydro, water, and meteorological or weather-driven drivers. So the shape of this head wall is going to be reflective of changes in how much water is pouring over the edge of this thing and what the temperatures are like and what the solar radiation is like. Is that true or not? Is there a way that we can connect these drivers to the shape of the head wall? The second hypothesis is this volumetric change. Long-term thaw slump evolution follows a predictable trajectory from initiation to stabilization. Those are the two things I want to focus on for the rest of today. This is a picture on the ground. That's a little camera for perspective. We're panning across here. If there was a person standing, they'd be a little shorter than that lump right there. And so this thing's about 300 meters across now, around 250 meters from the head wall down to the river. And you can see that it's a big muddy mess. And what's going on is that the wall wears back gradually through time, and these chunks of tundra fall off and end up down on the ground. So where are we, right? We're in northwest Alaska. I'll show a map here in just a second. Along the Selawik River, the mean annual temperature is -5 degrees Celsius with a mean annual precipitation of just about 25 centimeters. So just about that much precipitation all year. Definitely a lot less than around here. Arctic desert, it's often referred to as. It was initiated in 2004. That's when it started. And when it started in 2004, it started by the river bluff being worn back, then leading to a gully, which cut down into this river bluff, and then it grew back from there over time. It's now grown to be a pretty big thing, and there's a bunch of previous and ongoing work. It's 50 kilometers upstream of a spawning area for a massive whitefish called a she-fish or a canoe. This is the primary source of of diet for the people who live in Selawik village downstream. It's the #1 sort of food source, subsistence food source for them. And a guy named Ray Handers done a great job documenting the sort of age structure of those fish. The problem with understanding whether or not the slump affects the fish immediately is that these fish live to be somewhere between 60 and 80 years old. This is an extremely long-lived fish, which means that it takes a long time for them to mature. They do not come back to the river to spawn until they're 10 to 12 years old. And if I've told you that the slump started in 2004, if there was some impact on the juvenile fish, right? If spawning was impaired, we wouldn't really know it until after at least 2014. And from last year's survey, they think they might see something, but it's way too early to tell. And we can't quite tell whether or not there's been a diminish in recruitment of new recruits for spawning as a consequence of the sediment created by this. We've done some glacial geologic mapping in this area to understand the history and what sort of materials this slump is made out of. Pat, who's in the audience now, did a great examination of the sediment flux to river and how that varies over 24-hour cycles. High turbidity pulses and how they affect water quality, and the metabolism of the stream, or how energy is processed by all the organisms that are living in that stream. Amy Jensen, another graduate student with me, worked on comparing carbon fluxes, the greenhouse gases being released to the atmosphere, and the soil development or subsurface transformations in a chronosequence of slumps. One, the active one you've seen already, one that's been stabilized, and then we compared that to unaffected tundra. So we've got a number of different studies here, from glacial geology to stream ecology and water quality, including ones doing this sort of soil biogeochemistry. But I'm going to focus on these volume changes, these erosion changes. So here's Alaska. The red square that we're looking at here is where this study took place. It's in northwest Alaska along the Selawik River. The Selawik River drains out on the north side here of the Seward Peninsula, that's this part here, and out into the Chukchi Sea and off to the Arctic Ocean. In this place, a graduate student, Theo Barnhart, one of the 3 authors listed at the beginning of the talk, Theo went out here for 2 different years, in 2011 and 2012, and he took along with him this big, heavy, clunky laser that costs around $500,000, mounts it onto a tripod, and turns it on twice a day. He turns it on in the morning and in the evening, and scans at an extremely high resolution the topography of this feature. And when I say extremely high resolution, I'm talking about making a map like this, where the floor of the slump is composed of, somewhere between 10 to 15 million points. Okay? 10 to 15 million individual measurements of topography on the floor and head wall of the slump. We don't use this trees, the other stuff that we end up hitting, but we're looking at the floor and the head wall here. And so we basically have a measurement of every centimeter on the ground, what that elevation and position is for this. And he does this every 12 hours for about a month and a half, for 2 years during the summer season. And we can watch the slump change on that 12-hour cycle. So if we have a wet day, what's the response? If we have a hot day, what's the response? Right? If we have these different changes, what's the response? And that was what we were going after here on this project. To show this, I have some interval photography here that I'm going to show as a movie, and I have to grab my mouse and start this thing up. And you can watch the back wearing over, oops, that's not what I wanted to happen. Back here, play. Let me explain what you're seeing. You're looking at the head wall. Here's the floor of the slump. Here's the head wall. Here's the tundra up above. I'm going to play this multiple times. Start out by just looking at the tundra here. It sort of feeds off like a ticker tape. Oh boy, what's going on with this? I know it's going to work. It's just whether I can work it. Here we go. Okay, so you can see the tundra wearing back. As the wall goes back, the tundra is just sort of being fed away. Okay, the next thing I want you to pay attention to is the floor down here at the bottom. I'm going to play this again. And you can watch the products that are coming off of here. See how it's sort of gradually shifting and flowing and moving? You can use the plant as sort of tracers. And if I get in here and I'm really careful, I can sort of drag this thing back and forth and show you the kinds of events that occur. And this is a small scale one, but I want you to pay attention to this area right here as I do a little flipping back and forth here. Right here should be good. And I'm gonna, okay, and you can see that there's sort of a mass that just sort of fails and collapses and exposes the wall. So I don't know if you can see that. Are people able to see that okay? Yeah. As I flip back and forth like this? So what's going on is that this ground right here is becoming saturated and that it's essentially collapsing as an earth flow a little farther down into this flat area where it then stabilizes. Okay? Now this kind of behavior of accumulating over time and then failing, so this is just two images I'll flip back and forth in. This is 12 o'clock on some day in July in 2009, and then 4 o'clock just a few hours later. And I want you to notice, look at this big wet flat surface that's all filled in here.